Good morning, good afternoon, or good evening to everyone. I'm really excited to be able to talk to you today about my favorite topic, which is quantifiers. We're going to be looking at few, several, and many today. And we're basically going to be looking at the underlying semantics and using probabilistic models to represent them. So I'm sure most people know what quantifiers are, but just to give a working definition, a quantifier is a lexical item which denotes a quantity of entities. So I have a number of examples here with many. Melanie has many children, Melanie has many pairs of shoes, Melanie has many degrees, etc. And if we think about the meaning of these utterances, Melanie has many children, it's probably 5, 6, 7, 8 or more children. However, many pairs of shoes would be much more, right? Maybe 15, 20, 30 pairs of shoes. In the case of many degrees, it could be as few as 3 degrees, like a bachelor's, a master's, and a PhD is considered many degrees. And so we can see that the reference values for these quantifiers are quite variable. And by variable, I mean context dependent, right? So the overarching question for the talk is there some stable, interpretable underlying meaning of many, or do we just analogize to new contexts? All right, so in 1991, Clark had a first crack at the meaning of many, a core meaning for many, and he said that many is true if the quantified value is greater than or equal to some x min. So in the example of Melanie has many pairs of shoes, this would mean that Melanie has more than x min shoes, right? So we can see that the x min is highly context dependent. It'll be different for pairs of shoes or for degrees or for children or what have you. And one way that we can think about this x min is about our expectations, right? So Melanie has many pairs of shoes would mean Melanie has more pairs of shoes than we might expect her to have given the context. So this is a step in the right direction, but because the x min is very dependent on the context, there's different x mins for each individual context. We have a core meaning, but it's not necessarily a stable core meaning. So when we're thinking about expectations, one way that we can model expectations using formalism is using an expected value distribution. So it would look something like this. We have pairs of shoes on the x-axis and the probability or likelihood on the y-axis. And we'll have some sort of distribution over pairs of shoes. So in this case, it's most likely that Melanie has maybe 18 or 19 pairs of shoes, and it becomes increasingly less likely as we get to the order of 30, 40, 50 pairs of shoes. So Schöller and Franke in 2017 took the semantics proposed by Clark and tried to marry it with these expected value distributions. So we have the semantics that we've seen before. Many pairs of shoes is true if the number of pairs of shoes is greater than or equal to this x min. And if we have our expected value distribution here, we can plot the x min along the x-axis. So there's some x min, maybe it's 15 pairs of shoes, right? And anything greater than that is going to be true for many pairs of shoes. And the interesting thing that Schöller and Franke introduced is that we can connect this x min with the probability distribution using what we call a probability density threshold. So there's different ways to think about this intuitively. One visual way is just to see that the threshold is the area underneath the expected value distribution curve between 0 and our x min. Another way to think about it is in terms of percentiles. Probability curves have a total area of 1 underneath them. And so the theta many is going to be somewhere between 0 and 1. If it's 0.5, it'll represent basically the 50th percentile of pairs of shoes that Melanie might have, or 0.75 would be the 75th percentile. And the fantastic thing about this threshold is that we can apply it to new contexts. So we have a completely new context. Erin has many students in her class. Again, it's true if and only if the number of students is greater than or equal to some x min. And this x min is going to be different, right? Maybe it'll be 15 students, maybe it'll be 20 students. But the cool thing is that this theta many remains the same. So although the x min is greater in the case of students than it is for pairs of shoes, the area underneath the curve, the theta that we're looking at is going to remain stable. So it's a little bit higher here, it's a little bit longer here, but we have the same area and different X-mins. So Schöller and Franke look at many, and they also look at few. So using the same exact expected value distribution, we can have an X max for few, the maximum value for which few pairs of shoes would be true. And this is derived from a density threshold that we're going to call theta few. Same thing for students. Again, the X max is going to be a little bit larger given the shape of the distribution, but the theta few is going to remain stable. The main hypothesis that they work off of is that quantifiers like few and many have core meanings, right, represented by this theta few and theta many, which are stable across contexts. And this is in opposition to an alternate hypothesis in which each context has its own individual theta value. So for the main hypothesis, we have one theta few, one theta many for all contexts. The alternate hypothesis is that each context has its own individual theta. This is more in line with the Bayer-Clark semantics that we saw before. All right, so they perform a couple of experiments. The first experiment just asks participants about their expectations for different contexts, 14 different contexts. And they use these to form these expected value distributions. For the comprehension task, they then ask participants to respond with an interval when given a quantified utterance in context. So let me give you an example. We have Andy as a man from the US who had many cups of coffee last week. How many cups of coffee do you think Andy had last week? And participants are asked to respond with an interval, something like 18 to 21 cups of coffee. Finally, they implement the formal models in a Bayesian framework. So the hypothesis is operationalized as a generalized threshold model, where again, there's one theta few, there's one theta many for all contexts. Alternatively, with our alternate hypothesis, this is operationalized as our individualized threshold model, also known as the ITM, where there's a unique theta few and a unique theta many for each individual context. And they take these models, they fit them to the data in order to estimate these parameter values. All right, so their results. In terms of the metrics for the goodness of fit of the models, the individualized threshold model performed marginally better than the generalized model, but the difference was not significant. So the other sort of form of evidence that we can find for a stable threshold is in taking a look at the overlap in the credible intervals of the individualized thresholds. So if you look at this graph here on the x-axis, we have all of the different contexts, right? Pages in a book, passengers on a bus, and each of these colored lines represents the credible interval for the estimate of the theta value for that context. And we can see that these are highly overlapping. For both few and many, nearly all of the contexts share some threshold. So this is some weak evidence that they claim for a stable threshold, but they note the need for replication and extension, which is exactly where we come in. All right, so we're going to look at few. We're also going to look at many. We also are going to look at several. So several has pretty limited semantic literature. And so we're going to jump off of basically a lexicographic report from Merriam-Webster saying that several is more than two, but fewer than many. This implies that many would have a lower bound and an upper bound. So unlike few and many, just having a single bound, this is going to have two. So you can see again, the curves that we're used to, we're going to have an X max here derived from a theta max, and then an X min derived from a theta min. The truth value of several will be somewhere in between these two bounds. All right, so we're working with three hypotheses. The first is identical to Schöller and Franke's paper, that the theta values of many, several, and few are stable across all contexts. Additionally, because the meaning of several is positioned in opposition to many, we're hypothesizing that the lower bound of many is going to actually coincide with the upper bound of several. Additionally, because of pragmatic behavior of listeners in trading off between alternative utterances, we're also going to postulate that the upper bound of few is going to correlate with the lower bound of several. So essentially, if all of these hypotheses are true, few, several, and many are going to be existing in complementary semantic distribution. All right, so we have three hypotheses. What models do we need to create to test them? The first model is going to be the individualized model from Schöller and Franke. We're rejecting the stable threshold hypothesis and subsequently hypotheses 2 and 3, which rest on 1. For model B, we're going to adopt the generalized threshold model, which accepts the stable threshold hypothesis, but does not accept either of our additional hypotheses about complementary distribution. Finally, we have models C, D, and E, which all accept hypothesis 1 and represent the different possibilities for accepting or rejecting hypotheses 2 and 3. So we run 2 experiments, the first of which elicits expected value distributions, the second of which more directly probes participants' quantifier thresholds. So for experiment 1, participants saw a stimulus like you see here, and they're asked to provide intuitions for their expectations of Melanie owning 5 pairs, 9 pairs, 13 pairs, 17 pairs of shoes, etc. And they're giving these expectations on a likelihood scale of a 7-point Likert scale. They're going to see all of our 16 contexts. Most of them are taken directly from Schöller and Franke with a few tweaks, and we had 52 participants for this initial experiment. Taking all this data, we took the average Likert score for each integer for each context, and we fit a cubic spline that basically creates a continuous distribution for our expected value distributions. And of course, we're going to normalize so that the sum is 1 underneath. For experiment 2, participants see a prompt like the following. Melanie is a woman from the US who owns many pairs of shoes, and a question, how many pairs of shoes do you think Melanie owns? And so in this situation, we're asking them directly about their truth conditions for a quantified utterance. So many pairs of shoes, what is many pairs of shoes? What's the minimum and maximum value for which that could be true? Participants see all 16 contexts, and for each context, they see one of the 3 quantifiers in question. It's important to note as well, for many and for few, we're only looking at 1 bound, not 2. So for few, we're only looking at the upper bound. For many, we're only looking at the lower bound. Although there are some interesting things going on with the upper bound of many and the lower bound of few, I'm happy to talk about it in the Q&A. 137 participants for this experiment. All right, so we talked about our 5 models, A through E. We took the expected value distributions we created from our data from experiment 1, and we fit them to our participant responses from experiment 2. The goal of the modeling, again, is to estimate the theta values for each model, and we're fitting using Hamiltonian, Monte Carlo, and Stan. Results, this is the fun part. So are these theta stable across contexts? We're going to look again at the credible interval overlap for all contexts in model A. So just like the graph we saw with Schöller and Franke, we're going to look at the theta for each context and see if there's overlap or not. For our hypotheses 2 and 3, we're also going to look at our credible interval overlap, except in this case, we're not going to do context by context. We're going to look at the coincident thresholds versus the non-coincident thresholds and see if there's overlap there. Finally, for all of our hypotheses, we're going to implement the widely applicable information criterion. This is just a metric which tells us the goodness of fit of each model while trading off for model complexity. Okay, before I show you the credible interval overlap graphs, I want to give you some intuition for what we're looking at. On the y-axis here, we have our theta values somewhere between 0 and 1. And across the x-axis, you're going to see a number of different contexts, right? So this is an example of really good evidence for a stable threshold. We have all of our different contexts, they're highly overlapping, and there's a very effective way to draw a line through all of the intervals. So there is very likely a stable threshold here. An example of some evidence against our hypothesis would be something like this. So we see the credible intervals are very unoverlapping, right? There's no way to draw a line through all of them. We can get maybe 4 out of 10, but they're quite disparate. All right, so for our theta many, we actually see 15 out of 16 contexts sharing an interval. Fantastic, right? We do have one outlier here, which I believe is meals, number of meals cooked at home in a week. And there is something funny going on with the expected value distribution, so there's a reason that it's an outlier. Another thing to note is that this interval is quite large, between 0.41 and 0.45. 15 out of 16 of these contexts share that large interval. For theta few, 12 out of 16 contexts, still not bad, not quite 15, but you can see for the ones that aren't exactly overlapping, a lot of them are very close. Again, we see our usual suspect of meals and students, which have reasons why they're outliers. Then we go ahead and look at the lower bound of several. Again, 15 out of 16 contexts, fantastic evidence for a stable threshold. And again, we have water here, glasses of water, drinking in a day, I believe. And the expected value distribution for this is also a little bit funny. So there are reasons for these outliers. Finally, we look at the upper bound of several, which is our least consistent threshold. Only 10 out of 16 contexts share an interval. And again, there's a reason for this. Like we talked about before, there's a reasonable semantic argument to be made that several should only have a lower bound and not an upper bound. We did make the assumption that it had two bounds, but there's an explanation for why this is our least consistent threshold. Moving right along to our hypothesis 2, you can see here again, we have our thetas down on the x-axis and the values along the y. For models B and D, we had one theta for the upper bound of several and one theta for the lower bound of many. So these are separate, right? For models C and E in the center here, we had one threshold that was trying to account for both phenomena. And in all of the models, we see there's no overlap whatsoever between the theta many and the theta several max or a coincident threshold. So this is essentially pretty good evidence that we should reject our hypothesis 2. Essentially, we find the same thing for the upper bound of few and the lower bound of several. You can see the coincident thresholds are not overlapping with our individual thresholds. Sorry, I shouldn't say individual, but our separate thresholds, right? So hypothesis 3, we're also just going to reject. Finally, in taking a look at our widely applicable information criterion, we can see that model A performs the best, lower is better in terms of WAIC. However, models A and B have a high degree of overlap in their credible interval for the WAIC metrics. So again, this doesn't really tell us much about which model is performing better, although we can say for sure that models C through E are not seeming to fit as well. All right, so what are the conclusions here? For hypothesis 1, theta values are stable across contexts. We have inconclusive but quite promising evidence. I would say stronger than the evidence presented by Schöller and Franke. However, there's still further experiments necessary. Additionally, we see that the context stability of quantifier thresholds might exist along a spectrum. So we have our theta many and our theta several min were very consistent, right? Theta few is a little bit less so, and theta several max being even less so. So it's possible if we take a wider survey of lots of different quantifiers that we'll see a spectrum of context stability. And again, for hypotheses 2 and 3, we're pretty much going to reject them. Those models didn't do very well in their goodness of fit, and we don't really see any overlap in the credible intervals there. So with models C, D, and E out of the game, we're choosing between models A and B, and it looks like model B has the strongest evidence. So let's look at what the actual theta values were, right? If we're choosing model B, if we're going to move forward with it, what actually happened there? What are the estimates that we get? So for theta few, our estimate is 0.38. So again, you can think about that in terms of like the 38th percentile. So anything less than that is going to be considered few. For many, we actually find it's quite close to theta few. It's only about 0.4, but again, in the opposite direction, right? So anything greater than about 0.4 would be considered many. Interestingly enough, the lower and upper bound of several has a high degree of overlap for theta few and theta many. So we don't see this complementary distribution between few, several, and many like we expected, but more of a complementary distribution between few and many, with several overlapping both of those. Yeah, so you can see the truth conditions for several are between these two bounds. So what does this mean in context? We're looking now at cups of coffee in a week and students in a primary school class. So for our theta few of 0.38, we have 8 cups of coffee or fewer in a week would be considered few cups of coffee. And for students, 16 students or fewer would be considered few students. For many, it's very similar, but again, in the opposite direction. So about 9 cups of coffee or more would be considered many, and 18 students or more would be considered many. For several, we see anywhere between 7 and 13 cups of coffee is several cups of coffee. And then finally, for students, anywhere between 13 and 25 students It's very interesting as well to see that the lower bound of students here is basically the upper bound of poverty, right? So although the thetas are stable, we do see very heavily shifted X-min and X-maxes. All right, looking ahead, currently we're working on modeling pragmatic behavior a little more explicitly. Obviously, the coincident threshold hypotheses did not hold. So we're planning on implementing a rational speech act framework on top of the bare semantics. Additionally, we would like to investigate lots of different types of quantifiers, more colloquial quantifiers like a lot, a bunch, not too many, a good amount. And of course, as everyone has been saying today, cross-linguistic, cross-dialectal, individual variation work is very important and necessary. Yeah, thank you to everyone. I'm happy to answer any questions that you have. Feel free to reach out to me. I have my email and my academic Twitter on here. Thank you so much.